Single-turn prompt engineering is dead. The future of software architecture belongs to stateful agentic loop engineering. Babysitting an AI model by manually copy-pasting prompts is a temporary workaround. We are replacing manual prompts with stateful loops.
Agentic loop engineering transforms AI into reliable enterprise systems. But how does it actually eliminate the human from the loop? Because legacy single-turn prompt engineering fails to scale in production. It relies on massive cognitive friction and human babysitting to fix errors. Take a complex workflow, like asking an AI to generate a database migration script. In the old paradigm, an engineer manually inspects the raw output for syntax errors, then writes a follow-up prompt to try and fix the code. Instead, developers now build a persistent runtime environment to govern the AI. This environment automatically prompts the model and directly captures the raw tool output. But without a human babysitter, how does the system catch hallucinations? The environment executes the code and captures the machine logs, creating a stateful checkpoint, and automatically evaluating the progress against strict machine-verifiable criteria. If the criteria fail, the system passes those execution logs directly back into the model's context as a new prompt, forming a closed loop. So what exactly happens to that highly complex database migration script we mentioned at the very beginning? The loop autonomously tests and refines the code using those error logs until it compiles perfectly. Zero manual copy-pasting required.
Let's walk through the 5 sequential phases that every agentic loop executes, from trigger to completion.
How does an agentic loop solve problems autonomously? Unlike fragile linear scripts that crash, this engine adapts to failures. Imagine a GitHub webhook injecting a task to fix a broken database query. Phase 1, ingestion. The engine catches the payload, loading the task and strict system constraints. Phase 2, planning. Instead of one massive guess, it breaks the objective into manageable subtasks. Phase 3, tool execution. The agent runs actual SQL commands to fix the bug. This physically alters the database environment and captures the raw logs, a process called state mutation. But did the fix work? The engine routes the output to rigid, objective unit tests, known as deterministic evaluators. These evaluators answer one binary question: did this tool call achieve the subgoal? Because the test failed, it appends the exact error log and loops back to self-correct. This architectural feedback loop is called state reentry. It iterates until the goal is satisfied. So what exactly happens to that broken database query that triggered the original webhook in the very beginning? The task finally receives a secure 200 OK status, persisting the verified code state and exiting the engine cleanly.
Unbounded agent autonomy is a disaster waiting to happen. You must build circuit breakers into the loop.
Deploying an unconstrained AI agent in production is a catastrophic risk. A single hallucination can trigger an infinite loop, racking up massive cloud costs or corrupting a database. To fix this, we build a strict 3-layer architectural cage around the agent. It starts with layer 1. Because agents can't rely on temporary memory, every tool call is written to a permanent database. This is state management. If the model crashes, it resumes from the exact last verified state, preventing dangerous re-executions. But memory won't stop a runaway process. We need a runtime cage that enforces hard iteration caps and strict token budgets. This is layer 2, execution governance. Circuit breakers monitor for repeated errors, instantly shutting down rogue executions before budgets trip. For critical actions like database migrations, the system forces the AI into a dormant wait state, awaiting manual sign-off. This final failsafe is layer 3, boundary control. It packages a structured summary of the proposed changes, requiring explicit human cryptographic approval to proceed. So when a hallucination strikes, the bound agent simply hits its cap, saves its state, and waits for your review. With these boundaries, Wild AI becomes a predictable enterprise engine.
Let me break down the 3 core components that define every production-grade agentic loop.
Enterprise AI can't survive on single-turn chat prompts. To automate complex tasks safely, you need an agentic loop. Imagine a critical server failure triggers an automated SRE alert. An agentic loop resolves it using 3 non-negotiable pillars. Pillar 1 is the event trigger. The SRE alert acts as a webhook, injecting a structured input payload to kick off the execution sequence. Pillar 2 is the stateful execution engine. This persistent memory layer maps every single step into a database like Redis or Postgres. It meticulously tracks execution history, tool calls, and the exact step index of the loop. But what happens if the AI hallucinates or the server crashes mid-task? Because the state engine preserved the exact memory context, the loop resumes precisely where it left off. Which brings us to Pillar 3, the verifiable end goal. An agentic loop can never rely on the AI's subjective confidence to decide when it's done. It must collide with a deterministic, machine-verifiable end state, meaning it matches a strict JSON schema or passes automated unit tests to prove completion. And that critical SRE alert from the beginning, the loop confirms a 200 OK server status, safely executes the fix, and securely terminates. Stateful wait states let AI freeze high-risk tasks, but how do they pause indefinitely without breaking? AI models are unreliable execution threads. They cannot blindly execute irreversible actions in production. Take an enterprise AI agent tasked with autonomously transferring corporate funds. It breezes through the initial low-risk steps, autonomously gathering account details and calculating totals. But when it hits a high-impact boundary, it must stop. If it waited in active memory for human approval, a server crash would destroy the entire workflow. Instead, it enters a stateful wait state. The agent pauses its active execution and serializes its exact progress into a persistent database, going safely dormant. The frozen engine automatically extracts the proposed transfer amounts and code diffs, packaging them into an approval payload and routing it to a human engineer via Slack. The system stays entirely locked until a human signs off with a cryptographically verified signature. This strict boundary is called deterministic execution resumption. If rejected, it cleanly rolls back. But if approved, the state engine wakes up and unpacks the database. And what about that massive corporate financial transfer we started with? The agent resumes its exact path and safely executes the authorized transaction without dropping a single byte.
To transform unpredictable AI models into enterprise software, you must build strict loop boundaries across state, execution, and human control.
Autonomous AI agents execute complex tasks continuously. But what physical mechanisms stop a hallucinating model from destroying an entire system? Unbounded autonomy is a massive operational risk. One unhandled edge case can burn millions of tokens in minutes. Take a production AI agent trying to parse a corporate database that suddenly encounters a formatting error. To prevent an infinite loop, systems enforce hard iteration caps. After a strict limit, say 5 failed attempts, the runtime terminates the cycle. Since models can generate expensive outputs almost instantly, the environment also enforces a hard financial fuse. The millisecond an execution exceeds a hard cap, like a 50-cent budget, the fuse halts the environment. But what if the agent hasn't hit its 5-cycle limit or burned its financial budget, but hallucinates the exact same failing query again? Automated monitors track exact error patterns across iterations. If the model repeats the identical failing tool call twice, a deterministic circuit breaker physically severs the connection. Rather than silently failing, this shutdown freezes the runtime state and immediately escalates the incident to human SRE teams. And that hallucinating database agent from the beginning, the moment it repeats its broken query for the second time, the circuit breaker snaps shut, freezing the agent in its tracks before a single extra token is ever billed.
Loop engineering isn't one size fits all. Let me show you how to choose between code, low code, and no code.
Building a single AI agent is easy, but engineering a continuous, reliable agentic loop, that requires matching your architecture to the stakes. There's a 3-tier spectrum between absolute control and pure speed. First up, code-first architecture. Using frameworks like LangGraph and Python, you get absolute programmatic command. You build deep safety mechanisms that tell the AI exactly when to halt execution and precisely how to remember sensitive data between steps. It's strictly for mission-critical enterprise systems. The trade-off? Massive engineering overhead. Next, low code. These use canvas-based interfaces where you drag and connect pre-built blocks to form workflows. Platforms like N8N and Flowise accelerate team operations. You get the speed of visual building while still letting developers open a block and inject custom Python or JavaScript for strict verification. Finally, no-code tools like Zapier Central or custom GPTs. It's a zero-code drag-and-drop reality. perfect for rapid prototyping and personal tasks, but you surrender all control over data privacy and memory. Every architecture is a trade-off. You buy no-code speed with your data privacy or earn code-first's rigor through engineering time.
Let me show you a real-world production loop. An automated LinkedIn content publisher with built-in human approval gates.
How does an agentic loop execute complex, multi-step workflows without making catastrophic mistakes in production? It requires strict boundary control, ensuring unverified actions never reach the public. Take the LinkedIn content publisher, a 5-step automated architecture that replaces manual content creation. Step 1 wakes on a schedule trigger, ingesting topic data and audience personas to anchor its focus. Step 2 generates competing post angles and evaluates hook curiosity scores to select the best draft. Step 3 compiles matching visual assets, pairing custom graphics with the drafted copy into a complete package. But handing an autonomous agent the keys to a live LAST API is a massive production danger. To solve this, Step 4 routes the draft to a Telegram bot and completely freezes the system's memory. The system serializes its state and halts execution, a mandatory pause called a stateful wait state. The agent remains dormant until a human engineer taps Approve, granting cryptographic sign-off via Telegram. This approval wakes the system to resume execution, publishing the post directly via the LinkedIn API. The 5-step pipeline successfully completed its automated task, while the human supervisor merely tapped a single button to ensure the entire process remained safe and verified.
Stop prompting your models manually. Start engineering stateful, governed loops that turn AI into reliable production software. Is your engineering team building stateful AI loops or just prompt scripts? Let me know in the comments below.